So, in this video I want to discuss the problem of underdetermination in science, which I briefly referenced in my video on constructive empiricism a while back, so feel free to check that out. In any case, underdetermination is the idea that the evidence available to us may not be sufficient to establish that one particular scientific theory is necessarily correct. In other words, a finite body of observations, or evidence if you will, may be compatible with several and perhaps even infinitely many mutually incompatible theories. We can consider, for instance, the famous historical case of predicting the orbit of Uranus, which originally deviated from calculations using the framework of Newtonian mechanics. Now, this was solved by predicting the existence and location of a new planet, namely Neptune, thereby validating the Newtonian framework, but we could equally say here in the intermediate time frame, when this remained an open puzzle, that there existed not one but many mutually incompatible theories which could explain the same phenomena. Here, an observed planet would be one of these theories, but we could also include measurement errors, an incorrect auxiliary assumption, or evidence indicating that we needed to modify gravitational theory altogether, for instance. Hence, the problem of underdetermination obviously poses a problem for us, as it creates a problem for determining which scientific theory, if any, correctly really describes our reality. We are thus faced with a situation in which no single experiment may be capable of ruling out every alternative explanation, leaving scientists with a potentially large set of empirically equivalent or observationally indistinguishable theories. Bad luck indeed, it would seem. To take a step back, the problem itself has a long history in philosophy. The philosopher Leibniz, for instance, objected to Newton's conception of absolute space using an argument from underdetermination. For clarity, absolute space was a theory put forth by Newton, which claimed an unchanging, immovable background that exists independently of any physical objects or external events. To quote the man himself, absolute space in its own nature, without regard to anything external, remains always similar and immovable. Relative space is some movable dimension or measure of the absolute spaces, which our senses determine by its position to bodies. The problem for Leibniz with absolute space existing was that God could have created the entire material universe a few meters farther to the left, or giving it a different absolute orientation without producing any observable difference in the relations between material objects. There would therefore be several physically distinct but empirically indistinguishable descriptions of the universe. In effect, Leibniz used this very argument to challenge the idea that absolute spatial position corresponds to a genuine physical difference. We should observe here that it is not simply that infinitely many theories could explain a single observation, but Leibniz insisted that in addition, Newtonian absolute space appeared to introduce distinctions that could make no observable difference. The problem of underdetermination also popped up a great deal in the 20th century with the work of Quine and Duhem, but more on that later. For now, we organize the video in the following way. First, we here want to look at the problem of underdetermination itself and explain why it may lead to undesirable consequences. Second, we will consider several proposed responses to the problem and discuss an example. Finally, we will examine criticisms and consider the view that underdetermination is not as serious a problem at all as some philosophers have claimed. So let's do that. To start, we can distinguish three ways in which underdetermination might appear problematic. First, we will consider whether underdetermination creates a difficulty for scientific realism, since it appears to challenge the claim that successful science identifies the true underlying structure of reality. Second, we will consider the epistemic objection that when several incompatible theories fit all the available evidence, belief in any one of them may seem insufficiently justified. Finally, we will examine whether the existence of empirically equivalent theories makes scientific theory choice arbitrary or dependent on non-empirical considerations. The first argument, then, concerns the apparent conflict between underdetermination and scientific realism. If two or more incompatible or possibly infinite theories account equally well for all the available evidence, it may seem unclear how a scientist could be justified in believing that one theory is true, while the alternatives are false. Note here that this does not seem to pose a problem for other views in the philosophy of science, such as instrumentalism, since this view holds that a scientific theory is not a description about the world, but an instrument for organizing thoughts about observables, i.e. connecting and relating observational data. This is summarized in the following video snippet.
The scientific instrumentalist does not say we're getting knowledge, but rather merely that these theories are useful for some other purpose. Let's use an example. Imagine we're way back in ancient Greece, and we have two farmers. One of them is a scientific realist, and one of them is a scientific instrumentalist. The realist believes that the geocentric model is true and plants his crops based on it. Geocentric, remember, is where the sun goes around the earth. The instrumentalist, on the other hand, finds the geocentric model useful for planting crops and plants his crops based on that model, but does not believe that that model is the case. As you can see, he can still plant his crops just fine without having that belief, merely using the concept, and still remain rational.
So, in this case, the theory is not capable of being true or false, but capable of being useful or useless in the scientific context it is applied. Likewise, for the logical positivists, which it should be admitted at this stage are virtually non-existent. But in any case, in relation to the problem of underdetermination, they want to say something like that all competing theories are the same. That is, they will view a scientific theory as a collection of theoretical and observational statements where it is always possible for them to take this theoretical language and translate it into observational language. The resultant output of this translation is then that rival theories end up making the same claims about the world, where any rival theories making these same claims about observables will be numerically identical with each other. Thus, anytime we have a scenario where two rival formulations have exactly the same observational consequences, then any alleged difference between them may lack empirical significance, and in this framework we view the theories as being the same. Hence, by adopting the empiricist-logicist framework, assuming such a translation is possible between theories making these same observational claims, then there is no need to adjudicate among two or more competing theories. Lastly, for the constructive empiricists, they will not play the translation game, but rather place emphasis on the fact that we should firstly limit empirical attention to observables, where among competing theories, we should only believe that rival theories are empirically adequate, and by empirically adequate, we mean true regarding observables, such that it successfully describes what we can see and experience. Contrast this to the case for the scientific realists. They want to say something stronger, or act stronger if you will, by both wanting to choose an appropriate scientific theory among rival theories, as well as believing that this theory is at the very least approximately true about the world. If underdetermination is true, such that we suppose two theories, let's call them T1 and T2 for simplicity, both make exactly the same observable predictions, yet describe the unobservable structure of the world differently, then it follows that the available evidence cannot determine exactly which of the theories is true. We can also extend this problem to unobservables, which the realists are committed to. Then we have a problem of whether the evidence determines which description of the unobservable world is correct, where imagine for instance that every observation we make is compatible with the following three claims. A phenomenon is caused by particles, the phenomenon is caused by fields, the phenomenon is best described by a different mathematical representation without treating either particles or fields as fundamental. Hence, we are here in a case that if every possible observation is compatible with all three, the realist lacks a purely empirical reason for choosing one unobservable theory over the other. This last scenario here seems to fit well with the point we wanted to illustrate earlier, namely that when several incompatible theories fit all the available evidence, belief in any one of them may seem insufficiently justified. We could go even further here using this scenario and claim that these empirically equivalent theories make scientific theory choice even arbitrary or perhaps dependent on non-empirical considerations, such as choosing the unobservable explanation that fits with most scientific popular theories, or one that has a greater chance of obtaining funding, for example. In any case, we can obviously see the problem for the scientific realists, where we end up in a situation where there exists severe challenges to whether the evidence warrants the realist's stronger interpretation and commitments of science altogether. To end off this section, before heading over to some responses and proposed solutions, and capture underdetermination with the following useful diagram, in which we have the following. The same observable evidence, plus here incompatible accounts of unobservable reality, where we can infer here that we obtain no straightforward inference from empirical success to one true, or at least approximately true theory. To get into some responses, we will again consider the position of scientific realism, in which, from what we learned previously, took a rather hard beating when it came to underdetermination. But we might ask, are really things as bad as they seem? We should first here consider the fact that what we are really testing when we propose scientific theories is not so much scientific hypotheses individually isolated, but rather background assumptions, auxiliary hypotheses, experimental procedures, etc., plus the theory itself, such that we test these theories as part of a larger theoretical framework, which we can think of as a form of theoretical background scaffolding that has passed stringent scientific testing criteria previously, or rely upon solid theoretical groundwork, passing tests of course here as well. Hence, what we are really testing can be more thought of as a conjunction of scientific hypotheses, or package if you will. Then whenever we have two or more competing theories, again represented as T1 and T2, then we need to add in auxiliary hypotheses for each theory to obtain T1 plus A1 and T2 plus A2, for example, when we consider two theories here, where the obtained empirical equivalence may very well depend on carefully adjusting the auxiliaries accompanying each theory. Therefore, we can argue that the theories are not strictly equivalent, as we need to consider the auxiliaries in each case. But even if we grant that the auxiliary hypotheses are identical, i.e. A1 equals A2, we may argue that what we are really testing is not the independent approximate truth of individual theories, but rather a broader theoretical structure or research program where it is possible for competing theories to, at a given time, satisfy the same theoretical structure, yet they may differ in the future as the theoretical structure becomes more refined. Hence, such equivalence may be local to the present empirical testing, where we may expect theoretical and experimental refinements in the future. This sort of reasoning has often been discussed in philosophy of science in relation to the Duhem-Quine thesis describing the holistic character of testing, which I should make a video on in the future. I should also discuss the notion of research programs as introduced by Lakatosh in a separate video, but more on that later. Another response concerns appealing to abductive reasoning or inference to the best explanation, IBE, where given a situation where evidence does not deductively identify one theory, we may instead appeal to additional scientific virtues such as explanatory power, unification, simplicity, coherence with established science, predictive novelty, absence of ad hoc postulates, etc., where we argue that these virtues are not merely pragmatic, but serve as indicators that a theory captures real structures and causes, where we use these virtues to identify the best theory, that is, choosing between T1 and T2. More concretely, if we suppose that T1 and T2 account for the same existing observations, we may argue that T1 should nevertheless be preferred if it is the case that it satisfies more theoretical virtues, e.g. explains a broader range of phenomena, generates successful novel predictions, integrates more naturally with other well-supported theories, etc., which could be one example. A third response could be to consider a more minimal scientific realist approach, such as structural realism, where if we consider the unobservable example from before, we could argue that competing formulations can disagree about the nature of unobservable entities, while yet preserve the same underlying mathematical relational structure. This can be seen as an example where in relation to the problem of underdetermination, where we make the commitments to true or approximately true theories more selective by not committing to every object described by the theory T automatically, but rather to the common relational structure that successful theories provide. To get into some criticisms, first, we may again consider the scenario where we imagined testing scientific theories not in isolation, but rather as a package of theories represented in terms of the theory T and the auxiliary hypothesis A. We can argue that this still does not show that theories are approximately true, as in the case we are testing combinations, the combinations or conjunctions of T and AI, then it's still possible for the evidence E alone to not tell us which of the auxiliary hypotheses needs to be changed. In this case, we should therefore demand of the scientific realist to provide us with additional arguments explaining why normal scientific methods, which includes independent testing of auxiliaries and other scientific virtues, should reliably guide us toward approximately true theories to begin with. In terms of a response to IBE, we could argue from pessimistic induction using the observation that past scientific theories were thought to be the best explanations of their time, but turned out to be completely false, or stating that IBE cannot tell us which of the rival theories is approximately true, as multiple theories may satisfy these same virtues and explanatory power. Lastly, we could claim that when we evaluate competing theories, we are at each time point selecting only the best explanation from the ideas we're able to come up with. Hence, it's possible for the actual theory, or the truth theory, to not be in the group of evaluated options at all. This last point comes from Van Frazen, who we discussed earlier, see my video on constructive empiricism for instance. And this problem is known as the bad lot problem, for the central thesis is that we cannot assume an idea is true just because it is the best explanation available in a limited group available to us. Finally, responding to the structural realist, we might argue that this position works as a red herring of sorts, as it simply relocates the problem of underdetermination, as it is possible for multiple scientific theories to differ structurally, thereby not getting rid of underdetermination, we observe. Alternatively, we could make an argument from vagueness by claiming that structuralism is too vague in terms of properly defining what is meant by structure, i.e., are we talking about equations, causal structure, or perhaps symmetry, and how do we properly adjudicate between these proposals in terms of best possible theory? Before addressing point number 3, where we argue from the position that underdetermination does not pose a threat in science, we give an example which will help us in terms of distinguishing between the different positions that we have discussed so far in the video. The example we give here is the famous experiment in relation to Brownian motion conducted by Jean Perrin in early 20th century, which provided evidence for atoms, molecules, Avogadro's number, while serving as an important validator for Einstein's description of Brownian motion, where of course Brownian motion is also incredibly important in terms of understanding stochastic processes in mathematics, as well as playing an important role in finance, for example. In any case, the experiment considers small entities, such as grains suspended in water, which were originally observed to move irregularly earlier by Robert Brown while studying plant reproduction, where this phenomenon was explained by the fact that these small grains are continually struck by water molecules. Here, as previously mentioned, Einstein's theory of Brownian motion predicted a statistical relationship between factors such as temperature, the size of suspended particles, viscosity of the liquid in the experiment, etc., such that Einstein was able to give a mathematical account, which was then empirically validated in the experiment. More concretely, Perrin measured the motions and distributions of visible suspended particles, where his measurements agreed in a very accurate fashion with the statistical predictions given by Einstein. In fact, Einstein wrote 2 papers on Brownian motion, the first one in 1905, his famous miracle year, and the other in 1908, which concretely allowed for experimental testing, as done by Perrin. Yeah, and I linked some sources in the description where you can read more about the experiment. In any case, the importance of this experiment cannot be understated in terms of providing validation for Einstein's theories, confirming atoms and molecules, as well as serving as an important stepping stone in terms of unifying 2 fields in physics. To quote, "Eventually, the experimental evidence supporting Einstein's theory of Brownian motion became so compelling that the naysayers were forced to accept the existence of material atoms. His fundamental work on applying statistical methods to the random motions of Newtonian atoms also led to his insights into the photoelectric effect through the discovery of a critical connection between his statistical theory of heat and the behavior of electromagnetic radiation. This was the first step in his goal to unify the 2 fields." Now, how would we evaluate the experiment from the different positions we considered earlier? Well, we could observe that all 4 positions discussed so far make exactly the same measurements and calculations, such that their disagreement is really going to boil down to what philosophical conclusions should be drawn from the empirical success of the experiment. For instance, the scientific realist interprets the experiment as evidence for a real but unobservable molecular mechanism, giving the classic realist account. The constructive empiricist will accept everything the theory says about observable Brownian motion, but suspends belief about any unobservable mechanism or entities, such as atoms and molecules, which we cannot directly observe in the experiment. The logical positivist focuses on how molecular statements obtain scientific meaning through their connection to observable tests. Here, a classical logical positivist would consider exactly how theoretical terms could be completely translated into a purely observational vocabulary, and how this corresponds or maps onto the experiment. There are also more nuanced positions taken by logical positivists, where theoretical terms were treated as parts of a strict formal system historically that was only partially connected to observation through various formal correspondence rules. Lastly, the instrumentalist focuses on the theory's practical and predictive usefulness without treating truth about unobservable reality as necessary. He or she will therefore really only care about if the experiment validates strict predictions given by, in this case, Einstein's theoretical assumptions. The sort of strict emphasis on predictions is also summarized in this rather funny snippet.
The instrumentalist says, I have no concern. I just don't care what's really going on. I don't care whether the Earth is spinning or not. I just want something that'll will give me accurate predictions about where to point my telescope to see Mars in 10 days. And if it does that, that's all I ever wanted.
For this last section in the video, we look at a position some philosophers have taken where they claim the problem of underdetermination is not really a large or even problem at all. Here, while one may accept that evidence rarely entails one unique scientific theory, yet we still argue that its consequences are far less dire than what you would expect. The philosopher Larry Lawden, for instance, has observed that what he deems the weaker first claim of more than one logically possible theory can be made consistent with a given body of evidence does not entail the stronger second claim, namely that there are several incompatible theories that are equally well supported in terms of being scientifically credible and rationally acceptable. We can imagine, for instance, the competing theories being severely flawed, for instance, by claiming ad hoc assumptions, internal inconsistencies, or fail in other ways, such as generating novel testable predictions. The main point being here that it does not follow from the fact that several theories are compatible with the evidence that the evidence supports them equally well, such that we may perhaps safely accommodate for underdetermination in science. The alternative equivalent theories will therefore, according to Lawden, vary greatly in strength. To quote, Lawden usefully distinguishes a number of different dimensions along which claims of underdetermination vary in strength, and he goes on to insist that those who attribute dramatic significance to the thesis that our scientific theories are underdetermined by the evidence defend only the weaker versions of that thesis, yet draw dire consequences and shocking morals regarding the character and status of the scientific enterprise from much stronger versions. Of course, we could here counter Lawden by stating that he is correct that not every logically possible rival theory is equally credible. However, underdetermination does not require that every imaginable alternative be equally rational or good alternative. It requires only that there sometimes be two or more sufficiently plausible, incompatible theories that are reasonably supported by the available evidence. We will not move further here in counter-replies, but rather end this video here as it is long enough, but feel free to write in the comment section below what you think about the problem of underdetermination, and feel free to like, subscribe, and share the video, and I will see you in the next one. So, cheers!